Ever stirred sugar into your coffee and watched it just disappear? Or maybe you've heard that pop and fizz from a soda can.
Yeah, or even, why they salt the roads in winter.
Exactly. What makes these everyday things happen? It's actually, well, it's all chemistry, isn't it?
It really is. It's all about solutions and how substances interact when they mix. Today, we're doing a deep dive into the physical properties of solutions.
Right, and we're basing this on a pretty solid chemistry textbook and some really helpful lecture materials.
Our goal, really, is to unpack how things mix, what affects their behavior, and why understanding this stuff is so crucial.
Yeah, it's not just for exams. It relates to chemical reactions, biology, even processes in your own body. We want to simplify the complex bits and maybe show some surprising links.
Okay, so let's dive right in. First things first. What is a solution?
Okay, basics.
Well, basically, it's a homogeneous mixture, two or more substances mixed uniformly.
Homogeneous. Does that just mean it looks the same throughout, like salt water? Or is it deeper than that?
Oh, it's deeper. It means it's uniform right down to the molecular level. You won't find little clusters of salt here and pure water there. It's all perfectly mixed.
Gotcha. And in any solution, you've got the main part, the solvent.
Right, the solvent, that's the major component. And then you have the solute or solutes, which are the minor components dissolved in the solvent.
And we usually think of like salt and water, a solid and a liquid.
Mm.
But it's broader, right? You mentioned air before.
Absolutely. Air's a great example. It's a gas in gas solution. Nitrogen is the solvent, dissolving oxygen, argon, other stuff.
Huh, okay. And soda.
Carbonated water, that's CO2 gas dissolved in liquid water. Then you have liquid and liquid, like ethanol and water.
Like in vodka or something.
Exactly. And solid and liquid, like our salt water. But you can even have solid in solid solutions, like brass, that's copper and zinc mixed together.
Wow, okay. So solutions are pretty diverse. Now, what about how much solute is in there?
Good point. You can classify them. If you add just a tiny bit of sugar to tea and it all dissolves easily, that's an unsaturated solution.
Meaning it could hold more sugar.
Yep. But if you keep adding sugar until some just sits at the bottom, no matter how much you stir.
Then it's full.
Exactly. That's a saturated solution. It's holding the absolute maximum amount of solute it can at that temperature. And that specific amount, that's its solubility.
Okay, saturated. But then there's that really weird one, supersaturated.
Ah, yes. Those are fascinating. They actually hold more dissolved solute than they should be able to, more than a saturated solution.
How is that even possible? Are they stable?
Not really, no. They're quite unstable. You usually make them by heating a saturated solution, dissolving more solute, and then cooling it down really, really carefully.
Like it's balanced on a knife edge.
Pretty much.
Yeah.
And if you disturb it, say, by adding just one tiny seed crystal of the solute,
Whoosh. Does it all come crashing out?
it often does. You see rapid crystallization. All that excess solute suddenly precipitates out because the solution is scrambling back to its stable, saturated state. It's a great visual.
That visual really hints at what's happening with the molecules, doesn't it? The dissolving process itself.
It does. The core process is called solvation. That's where individual solute particles get separated from each other and then completely surrounded by solvent molecules.
And there's energy involved in this, right? It's not just mixing.
Definitely energy. You have to consider three main interactions. First, the solute-solute interactions. You need energy to break those apart.
Like pulling the salt ions away from each other.
Exactly. Second, the solvent-solvent interactions. You need to make space in the solvent, push those solvent molecules apart a bit. That also takes energy.
Okay, so steps 1 and 2 cost energy. They're endothermic.
Usually, yes. But then third, you have the new solute-solvent interactions forming. When the solvent surrounds the solute, this step typically releases energy. It's exothermic.
Ah, so the overall process, dissolving itself, could be either endothermic or exothermic, depending on how those energy costs and releases balance out.
Precisely. Some things feel cold when they dissolve, some feel warm.
But energy isn't the whole story, is it? There's something else driving things to mix.
Right. You absolutely have to consider entropy.
Okay, entropy, the measure of disorder, randomness.
Sort of. A better way to think about it is how spread out or dispersed energy is. Nature tends towards states where energy is more spread out. Entropy tends to increase.
Things like to get messy, basically.
Well, you could say that. Think about gases. Two different gases in separate boxes. Open a connection, they mix automatically, right?
Yeah, instantly.
Even if there's no energy change, no heat released or absorbed, They mix because the mixed state allows the molecules and their energy to be more spread out over a larger volume, higher entropy.
So that drive towards higher entropy, more spreading out, is a powerful force on its own.
Incredibly powerful. It can even make processes happen that cost energy overall, ones that are endothermic.
Yeah.
Like ammonium nitrate dissolving in water. The solution gets noticeably cold, but it still dissolves readily because the increase in entropy is so favorable.
Wow. So the energy balance and the entropy change together determine if something dissolves.
Exactly. And this leads us to a really useful rule of thumb, like dissolves like.
Ah, yes, the classic chemistry mantra.
It's simple but powerful. It just means substances with similar intermolecular forces, the attractions between molecules tend to dissolve in each other.
So things with similar stickiness mix well.
Kinda, yeah. Non-polar things like carbon tetrachloride and benzene, they both rely mainly on weak dispersion forces, so they mix easily.
Okay. And polar things, like methanol and ethanol.
Both polar, both can hydrogen bond. They mix perfectly. In fact, when liquids mix completely in any proportion, we call them miscible.
Miscible, got it. So quick test. If I have nonpolar bromine liquid, would it dissolve better in polar water or on polar benzene?
Non-polar bromine and non-polar benzene, definitely. Like dissolves like
Okay, what about something ionic like sodium iodide, water or benzene?
ionic compounds are extremely polar, you could say. They dissolve best in very polar solvents like water. Water molecules can surround the positive sodium ions and negative iodide ions effectively. Those are strong ion dipole forces.
Makes sense. So the rule holds up. Okay, so we know why things dissolve, but chemists always need to know how much solute is there. Concentration.
Absolutely critical. It's the amount of solute compared to the solvent or the total solution. And we have several ways to express it.
Let's run through the main ones. Molarity is a big one, right?
Yeah, molarity, capital M. That's moles and solute per liter of solution. Super common in labs because measuring volume is easy.
Okay. Then there's mole fraction, chi.
Mole fraction. That's just the moles of one component divided by the total moles of everything in the mixture, often used for gas mixtures or relating to vapor pressure.
And then one that sounds similar but is different, molality.
Molality, lowercase m. This one is moles of solute per kilogram of solvent. Note, solvent mass, not solution volume.
Kilogram of solvent. Okay, that's a key difference.
Yeah.
And then there are percentages.
Yeah, percent by mass.
Yeah.
Mass of solute over total mass of solution times 100. Simple. And for really tiny concentrations, you hear parts per million ppm or parts per billion ppb.
So why so many different units?
Different uses. Molarity is great for titrations, mole fraction for gas laws. But molality and percent by mass have a really important advantage.
Which is,
They don't change with temperature.
because mass doesn't change when you heat or cool something, but
Yeah.
volume does.
Exactly. If you heat a solution, it might expand slightly, changing its volume and therefore its molarity. But its molality, based on mass, stays the same. Very important for precise work.
That's a really common point of confusion, isn't it? Molarity versus molality.
It is. For very dilute water solutions, they're often numerically close, so people get complacent. But take something like rubbing alcohol, 70% isopropyl alcohol by mass.
Yeah.
The molarity is about 9.2 m, but the molality is nearly 39 meters. A huge difference. Units matter.
Wow, okay. Message received. Now, what actually affects solubility itself? Like, can we change how much dissolves?
Oh, definitely. Two big factors, temperature and pressure.
Let's start with temperature. How does that usually affect dissolving, say, a solid in a liquid?
For most solids, solubility increases as temperature goes up. Think dissolving sugar in hot tea versus iced tea. Much easier in hot tea.
Right. More dissolves.
Though it's not universal, every solid has its own unique solubility curve, how its solubility changes with temperature. Some change a lot, some barely at all.
Okay. What about gases dissolved in liquids?
Yeah.
Like the CO2 in soda.
Opposite trend. For gases, solubility decreases as temperature increases.
Really? Why is that?
Higher temperature means the gas molecules have more kinetic energy, makes it easier for them to escape the liquid phase. You see this if you leave cold water out as it warms, bubbles form. That's dissolved air coming out.
Huh. And does this have real-world consequences?
Oh, absolutely. Think about thermal pollution. If a factory dumps warm water into a river, that warmer water holds less dissolved oxygen.
And fish need oxygen.
Exactly. And warmer water often increases their metabolism, so they need more oxygen when less is available. It can be really damaging to aquatic ecosystems.
A clear link between basic chemistry and the environment.
Mm.
Okay, what about pressure? Does that affect solubility?
Not much for solids or liquids, but for gases. Hugely important.
Ah, this must be where Henry's law comes in.
Precisely. Henry's law basically says the concentration of a dissolved gas is directly proportional to the partial pressure of that gas above the liquid.
So more pressure above, more gas dissolves.
Yep. The equation is simple. C opal C. C is concentration, P is partial pressure, and K is the Henry's law constant specific to the gas, solvent, and temperature.
And the classic example is?
Carbonated drinks. They seal the bottle under high CO2 pressure. That forces lots of CO2 into the liquid.
Then you open it, pressure drops.
And the CO2 concentration is suddenly way too high for the lower pressure, so it rushes out as bubbles. Fizz! That's Henry's law in action.
Simple, elegant, and explains my soda. Okay, now let's shift gears a bit. There are these properties of solutions that are, well, kind of weird. The colligative properties.
Ah, yes. These are fascinating because they don't depend on what the solute is, just how many solute particles there are.
So it doesn't matter if it's sugar molecules or salt ions, just the total number of dissolved bits.
Exactly. It's all about the numbers. And there are four main ones we look at.
Okay, what are they?
Vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure.
All right, let's take them one by one. Vapor pressure lowering. What's happening there?
Okay, remember Raoult's law. It says the vapor pressure of the solvent above a solution is lower than the vapor pressure above the pure solvent.
Why? What are the solute particles doing?
It goes back to entropy again, partly. Adding solute increases the disorder, the entropy, of the liquid phase. This makes the liquid state slightly more favorable compared to the gas state. Fewer solvent molecules escaped into the gas phase, hence lower vapor pressure.
Okay, lower vapor pressure. How does that lead to the next one? Boiling point elevation.
Well, boiling happens when the vapor pressure equals the surrounding atmospheric pressure. If the solution's vapor pressure is lower to start with, you need to heat it to a higher temperature to get its vapor pressure up to atmospheric pressure.
Ah, so it boils at a higher temperature. Makes sense.
And there's a formula. The TB equals KBM. The change in boiling point, TB, equals a constant KD times the molality.
And we use this, right, like antifreeze.
Exactly. Ethylene glycol in antifreeze raises the boiling point of the engine coolant, stops it boiling over in summer. Also, adding salt to water raises its boiling point slightly.
Okay, so boiling liquid goes up. What about freezing?
That goes down. It's freezing point depression. Solutions freeze at a lower temperature than the pure solvent.
Lower. Why?
Again, think entropy. The solution is more disordered than the pure solvent. To freeze it, to make it form an ordered solid crystal, you have to remove more energy, go to a lower temperature to overcome that disorder.
So it's harder to freeze, and the formula is similar.
Very similar. TFF, KFM, change in freezing point equals a constant KFF times molality.
And this is the other job of antifreeze, right? Stopping the engine freezing in winter.
Yep, and it's why we salt the roads. The salt dissolves, lowers the freezing point of water, and melts the ice as long as it's not too cold.
Okay, that covers three. What's the last one? Osmotic pressure.
Right. This involves osmosis. Osmosis is the net movement of solvent molecules across a semi-permeable membrane.
A membrane that lets solvent through, but not solute.
Correct. The solvent moves from the side with lower solute concentration, more dilute, to the side with higher solute concentration, more concentrated.
Trying to even out the concentrations.
Essentially, yes.
Yeah.
And osmotic pressure is the pressure you'd need to apply to the more concentrated side to stop that solvent flow.
Okay. And there's a formula for this too.
Yep. MRT. Osmotic pressure equals molarity. M times the gas constant, R times the absolute temperature, T.
And this is hugely important in biology, isn't it?
Critically important. Think about IV fluids given in hospitals. They have to be isotonic with your blood plasma.
Isotonic, meaning same osmotic pressure.
Exactly. Same concentration of solute particles, roughly 0.3 m, which gives about 7.6 atmospheres of pressure at body temp. If the IV fluid was hypotonic, less concentrated than blood.
Water would rush into the blood cells.
Right, they'd swell up and burst. That's called hemolysis. Very bad.
And if the IV was hypertonic, more concentrated?
Water would rush out of the blood cells. They'd shrivel up. That's crenation. Also very bad. So the concentration has to be just right.
That really highlights the importance. And dialysis uses this too.
Yes, hemodialysis uses a semi-permeable membrane to let waste products diffuse out of the blood into a carefully prepared dialysate solution, while keeping larger essential things like proteins and cells in the blood. It relies on these concentration differences.
Our sources even mentioned a case where impurities like fluoride in the dialysate caused poisoning. Shows how precise it needs to be.
Absolutely, and even food preservation uses it. Curing meat with salt or sugar draws water out of bacterial cells by osmosis, causing crenation and stopping spoilage.
Ancient wisdom, modern chemistry. Now, we've mostly talked about solutes that just dissolve as whole molecules, non-electrolytes. What about things like salt electrolytes that break apart into ions?
Great point. If something like NaCl dissolves, it forms Na plus and Cl ions. That's 2 particles in solution for every 1 NaCl unit you added.
And since colligative properties depend on the number of particles.
Electrolytes have a bigger effect. We use the Van Hoff factor I to account for this. For a non-electrolyte like sugar, I equals 1. For NaCl, theoretically, I equals 2. For Na2SO4, which gives 2 Na plus and 1 SO42, you'd expect I was 3.
Theoretically, does it not always work out perfectly?
Often, especially in more concentrated solutions, the measured I value is a bit less than the ideal value.
Why would that be?
It's due to ion pairing. Oppositely charged ions in solution can sometimes attract each other strongly enough to act like a single unit for a short time, rather than 2 or 3 completely independent particles. This reduces the effective number of particles.
Ah, so they kind of stick together sometimes.
Briefly, yes. So the colligative effect is slightly less than you'd predict based on simple dissociation.
So we modify the formulas.
Exactly. They become ATF, IKFM, ATB, IKBM, and SKMRT. You include the actual or experimental I factor.
And these properties aren't just descriptive. We can use them for calculations, right? Like finding molar mass.
Definitely. Freezing point depression and osmotic pressure are particularly useful for determining the molar mass of unknown non-electrolytes because the changes are relatively large and easy to measure accurately.
And even for electrolytes.
You can use them to figure out the percent dissociation of, say, a weak acid. How much did it actually break apart in solution at a given concentration? It's a powerful analytical application.
Okay, one last area. What about stuff that's not quite a true solution, but not just a chunky mixture either? Colloids.
Right, colloids are kind of in between. They're dispersions of particles larger than typical dissolved molecules, maybe 1 to 1,000 nanometers spread throughout another substance.
So bigger particles, but they don't settle out like sand in water.
Correct. They stay dispersed, but the mixture isn't truly homogeneous at the molecular level like a solution is.
And we see these all the time.
Oh, yeah. Fog, smoke, those are aerosols. Whipped cream, styrofoam, those are foams. Mayonnaise is an emulsion. Milk of magnesia is a sol. Jelly is a gel. Even things like ferrofluids, magnetic nanoparticles, and liquid.
Lots of examples. Is there an easy way to tell if something is a colloid or a true solution?
There is. It's called the Tyndall effect. Shine a beam of light through it.
Yeah.
If you can see the beam path through the liquid, it's a colloid. The larger colloid particles scatter the light. True solutions don't do that. The light passes straight through unseen. Think headlights in fog.
Ah, visible beam means colloid. Simple. And within colloids, there are different types based on water interaction.
Yes, especially in water. You have hydrophilic, water-loving colloids, like proteins that fold so their water-friendly parts are on the outside. They're stable in water.
And the opposite.
Hydrophobic, water-fearing. These aren't stable in water by themselves. Their particles would clump together.
So how do they stay dispersed, like in milk of magnesia?
They need stabilization. Often, ions stick to the surface of the particles, giving them all the same charge so they repel each other. Or they might have hydrophilic molecules attached that help them interact with water.
Like putting a water-friendly coat on a water-fearing particle.
Exactly, and this leads to emulsification. That's when you use an emulsifier to stabilize a colloid, usually a mixture of 2 things that don't normally mix, like oil and water.
Soap. Is soap an emulsifier?
The classic example. Soap molecules have a long, nonpolar tail that dissolves in grease and oil, and a polar head that dissolves in water, so they surround tiny grease droplets, making them effectively water-soluble so you can wash them away.
Brilliant. Does this happen in biology too?
Absolutely. Bile salts from your liver do the same thing in your intestine. They emulsify the fats you eat into tiny droplets.
Why?
It vastly increases the surface area of the fat, making it much easier for enzymes to break it down so you can digest it and absorb fat-soluble vitamins. It's essential for digestion.
Incredible. So we've really covered a lot of ground today.
We have. From basic definitions, solute-solvent interactions, the role of entropy.
Concentration units, factors affecting solubility like temperature and pressure with Henry's law.
Then the colligative properties, vapor pressure lowering, boiling point elevation, freezing point depression, osmotic pressure, and the Van Hoff factor for electrolytes.
And finally touching on colloids and emulsification.
It really shows how these principles connect everything from lab chemistry to biology to everyday life.
Yeah, it's not just abstract stuff. It explains why antifreeze works, how IV drips keep patients safe, how we digest food, why soda fizzes.
So maybe the next time you see one of these things, salting roads, making coffee, whatever, you'll think about that molecular dance happening.
That invisible world of dissolving particles and the forces governing them. It really does give you a new appreciation for the chemistry all around us.